For each of my recent quantifying biological age videos, I've also posted data for cardiovascular fitness-related metrics, including resting heart rate and heart rate variability. So note that although these data correspond to a blood test, I have a lot more data that goes back all the way to 2018. So the focus of this video will be analyzing year-to-year changes for both resting heart rate and heart rate variability. So starting with resting heart rate, I started tracking that in August of 2018, and this is data that goes through the end of 2021, so December 2021. And as you can see by the end, I have 1,240 days of data for both resting heart rate and heart rate variability. So starting with the data for 2018, we can see that my average resting heart rate was about 51 beats per minute, 50.9 BPM. And note that my fitness tracker, and I wear Whoop, I'm not sponsored by them. Other fitness trackers can measure resting heart rate and heart rate variability similarly. Note that it records it automatically during the last sleep cycle, which takes away the human error in quantifying this stuff myself. So going from 2018 with an average resting heart rate of about 51, in 2019 my average was 48.9, and note that each of these circles corresponds to 1 day of data. And then in 2020, I further reduced my resting heart rate to 48.1, and in 2021, my average daily resting heart rate was 47.4 beats per minute. Now we can evaluate whether these resting heart rate values are significantly different from when I started in 2018 by using a 2-sample t-test, which is what I did. And when looking at the p-values for comparing each year versus 2018, we can see that each year I was able to significantly reduce my resting heart rate when compared with the 2018 data. And that's what's noted there. So is the resting heart rate, though, going in the right or wrong direction? So to assess that, let's have a look at how resting heart rate changes during aging. And this is Whoop data. Since I wear Whoop, I think it makes sense, at least to start, to look at Whoop users to compare me against other Whoop users in terms of aging-related changes. So resting heart rate increases during aging for both women in red and for men in blue, and I'm only going to focus on the data for men as that directly applies to me. So we can see that age-related change there for men with values of a little bit below 54 beats per minute for a 20-year-old that increased to above 56 beats per minute for a 50-year-old. And note that this chart only goes from 20 to 50 years old. So for my chronological age, based on the population average, I should expect to have a resting heart rate that's greater than 56 beats per minute. In contrast, my resting heart rate for 2021 was a little bit above 47 beats per minute. So by extrapolation on this graph, I could posit that my resting heart rate may be indicative of youth. Also, I've resisted the age-related increase for resting heart rate, at least that age-related increase that goes from 20 to 50 years. And there's a but in this story. So is the declining resting heart rate indicative of cardiovascular aging? So why would I think that? So whereas the Whoop data goes from 20 to 50 years, this is Fitbit data, and this is published, and I'll put the link to this paper in the video's description. So we're looking at average resting heart rate on the y-axis plotted against age, and although the age range goes from 20 to 50, it also goes from 50 to 85, so it goes beyond the Whoop data. So in agreement with the Whoop data, we can see that resting heart rate increases for both women in green and for the men in blue up to 50 years old. And then after about 50, we can see that resting heart rate then declines all the way up to 85 years old. So how can we know if a declining resting heart rate is indicative of better or worse cardiovascular function? And evaluation of resting heart rate in conjunction with heart rate variability can help assess overall cardiovascular fitness. So what is heart rate variability? Just as a brief introduction to that. So it's defined as the variation in time in between successive heartbeats. So what that means is the assumption is that with a heart rate of 60 beats per minute, is that the heart rate beats exactly 1 time per second. But that's not true. There's variability in that how often that the heart beats. So it may be 0.9, 1.1 seconds, and that variability is then calculated as the heart rate variability. So in this case, as shown by the picture here, the variability for the time in between beats was 859, 793, and then 726 milliseconds. And when calculating the heart rate variability using the RMSSD calculation, you get a heart rate variability of 67 milliseconds. So what's my data? And again, the Whoop tracks both heart rate variability and resting heart rate. So I have data that goes all the way back to August of 2018, and this is more than 1,200 days of data. So when I first started in 2018, my heart rate variability was 47.3. And I should mention too, at no point was I sedentary during any of these years. I've always been physically active. Back in 2018, I was walking at least 10 to 15 miles a week as to get to work. It's a 1 mile walk each way. So walking at least 2 miles a day, every day, or at least 5 days a week. So getting up to 15 miles a week, including walking on the weekends, plus regular strength training 2 to 3 days a week, at least an hour each session. So with that in mind, my heart rate variability in 2018 was 47.3. I was able to increase that to 56.2 in 2019. I increased it further. And then again, this is the average daily heart rate variability. So each, 365 days of data, the year average. So I increased it in 2020 to close to 58 milliseconds, and then it had a little bit of a dip in 2021, somewhere around 52 milliseconds. And then when comparing each of these years against 2018 using a 2-sample t-test, we can see that each year was significantly different from 2018. So each of the years, 2019, 2020, 21, were each significantly different and significantly higher when compared to 2018. And that's what's noted there. So let's take a look at how heart rate variability changes during aging to put these data into more context. And again, this is WHOOP data. So we're looking at heart rate variability on the y-axis plotted against age. And in this case, for some reason, their data goes up to 65 years. So when looking at the high end of the range, as noted there for men, and the data for women in yellow is very similar. So in youth, heart rate variabilities at the high end of the range can be as high as about 110 milliseconds that then get cut in half in 65-year-olds to around 60 milliseconds. Similarly, the median value goes from about 80 in 20-year-olds to somewhere around 40 in 65-year-olds. And at the low end of this range, values of about 60 in 20-year-olds dip to less than 30 in 65-year-olds. So based on this data, it should be pretty clear that heart rate variability declines during aging. So from my data, for the more than 1,200 days of data that I have, my average heart rate variability is 54.3 milliseconds. So to answer that question, how can we know if a declining resting heart rate, which is true in my case, is indicative of better or worse cardiovascular function when considering that my heart rate variability over this 3+ year span is above the median for my age? The median here, although I haven't indicated it, is somewhere around 42 milliseconds for my age group. So when considering I'm above that, one could argue that my cardiovascular function has improved since 2018, resisting age-related changes for both resting heart rate and heart rate variability. Now, if the resting heart rate reduction that I've experienced over that 3+ year period was in conjunction with a relatively low heart rate variability, for example, below the median for my age, so below 42, that would suggest worse cardiovascular function. So having a low resting heart rate and relatively low heart rate variability would suggest worse cardiovascular function. Now, it's not all sunshine in my data. As you can see, my data from 2019 and 2020 was much higher than 2018, and my 2021 data is significantly below the 2019 and 2020 data. So this shows that I definitely have room for improvement. So 2022 is potentially a big year. Will my data continue to get worse from 2021, or can I reformulate my exercise approach to get back to the data in 2019 and 2020 in 2022? All right, that's all for now. If you're interested in more about my attempts to biohack aging, check us out on Patreon. Thanks for watching. I hope that you enjoyed the video. Have a great day.